Okay, welcome back to Flight Software Workshop. Our next speaker is our keynote speaker for today, which is Kevin D. Bell, Vice President, Space Program Operations of the Aerospace Corporation. Kevin D. Bell is Vice President, Space Program Operations, the Space Systems Group at the Aerospace Corporation. Bell was appointed to this position on April 1st, 2017. In his role, Bell works directly with the Air Force, government, and industry partners to develop military satellites and to advance national security space systems. He assists with the development of space system requirements, provides schedule, cost, risk assessments, and solves systems development problems. Bell oversees 4 major mission areas: communications, surveillance, weather, and navigation. Bell joined Aerospace in 1992 as a member of the technical staff in Vehicle Systems Division of the Engineering and Technology Group, ETG. Most recently, Bell was General Manager of the Imagery Programs Division, National Systems Group, and prior to that, he was General Manager of Systems Engineering Division in ETG. Bell has also supported the Air Force, NASA, Commercial Ventures, Missile Defense Agency, and the National Reconnaissance Organization customers, serving as Systems Director of the Space and Directed Energy Technology Directorate, Principal Director of Missile Defense Division, Systems and Technology Subdivision, and Principal Director of Advanced Research and Engineering, Advanced Technology Division, among other interesting responsible positions within the corporation's National Systems Group. Prior to joining Aerospace, Bell held positions in industry, academia, and at the NASA Ames Research Center. The Aerospace Corporation is an independent, nonprofit organization dedicated to the objective application of science and technology toward the solution of critical issues affecting the nation's space program. Kevin's talk is entitled "An Agile Space Enterprise to Keep Pace with Technology and the Threat." Kevin.
Thanks, Chris. Well, good morning, and I guess afternoon and evening, since we're on a virtual global platform. So it's interesting. Chris probably should paraphrase some of that intro or bio, but you noticed software never really came up in the bio. I think the last really big code program I had was probably written in Fortran. Although I did play with DSpace for a while and some control algorithms, but then we were able to use AutoGen, and I decided at that point no need to code. So I thought, what am I gonna talk about at a flight software group, our workshop? And what I thought I'd talk about is I find myself. I actually started my career in aerodynamics, and I find myself now almost totally dependent on microelectronics and the software that rides on top of them. Everything we do is obviously driven by software, and it's been interesting to see that evolution in the space sector. So I thought I'd talk about why I think it's actually an incredible time to be in flight software and to be in space in general right now. I mean, maybe it's the same in all industries, but I feel like the ground is shaking under us in the space sector. We have incredible emerging and maybe already emerged commercial markets that are developing, that are deploying new technologies. And I won't name them all. We'll talk about a few of them later, but you're all aware of what's going on in the commercial sector, both in launch, on the ground systems, and of course in space. And space is kind of democratized in the sense that there are a number of global players on the stage now who weren't necessarily there just a decade or two ago. Almost anybody that wants to build a CubeSat can get into space now. And while all that's going on, the space industry isn't quite ready to give up these legacy exquisite systems. I mean, I think even with Starlink and OneWeb out there flying, we're not ready to jump off of our geosynchronous SATCOMs. And certainly in the DoD and in the intelligence communities, not just in the US, but globally, some of these legacy exquisite systems are absolutely essential, and they provide a capability you just can't get out of the commercial sector today. Some of these systems are just assumed, right? When was the last time you thought about the global positioning system being available? You just assume when you turn your phone on, it's going to be there. Likewise, for our missile warning systems, which have been there day and night, those systems have very, very, very little downtime. I mean, I think I can remember 2 GPS satellites in the last decade that were down for short periods. Maybe you read in the press the missile warning system that was essential in getting our soldiers underground in Iraq just last year. We count on those systems being there 24/7, and likewise for our comm links and being able to get our communications through to our systems deployed around the world. But I do think it's like there's an incredible amount of change coming on, and these systems that might have been more passive are becoming much more dynamic, much more responsive to technology change, threat change, to just the need. They're much more switched, they're tasked, there's complex mission managers, there's real-time response. All of this great technology has also changed the threat posture in space. For decades, we really were not that worried about someone threatening a space system. That's really changed in the last 5 or 10 years. You've heard about the Russian satellite, probably. Hopefully you've read that in the press, as it did some prox operations around one of our satellites in Leo. You've certainly heard about GPS jamming. Maybe you've even seen the recent articles on GPS spoofing in certain regions of the world. The Indian satellite intercept was front page news. That's all stuff in the last couple of years. We didn't think about that just a decade ago. And so this also really ratchets up the need for the space systems to be agile and to be responsive, not only to the change in technology, but to the change in the environment they operate in. And I really think that's where software, flight software in particular, comes in, because it's the one thing that you can change pretty quickly. We're not positioned well right now to change it quickly. And I'll talk some about what I think we need to do as an industry to be able to deploy software baseline changes in a much quicker and agile fashion. But really the overall space enterprise is limited by the speed of code. How quickly we can move code and move software into the system is what governs how quickly we can flex the space enterprise. So that's kind of what I talk about, given my more broad background. I thought I'd start with a little background on aerospace and I thought I'd try to do that through the eyes of software, through the generations. And then I'd talk some more about these drivers that I mentioned in the introductory there, and how software really is an essential enabler. And then I thought I'd conclude with just a quick description of a prototype we've been building over the last year called Slingshot, which is just a 27U CubeSat. It's kind of our next generation platform. If you've followed our programs, we've launched probably 40, 50 CubeSats over the course of the years, and we're instrumental in kind of standing up the CubeSat modular baseline and some of the standards associated with CubeSats, and even established something we call LaunchU and several of the modular launch interfaces. So I thought I'd conclude with that. But so let me start with a quick background on aerospace and how I see software migrating. We can go ahead and go to the next slide, please. So as Chris mentioned, we're a nonprofit federally funded research lab. We've been around for 60 years, really since the dawn of the space era. We actually spun out of TRW. Most people don't know that. At the time, TRW was providing advice to the government and competing for government contracts, which didn't pose well for non-conflicted advice. So since that time, we've been operating as a nonprofit corporation, and we provide most of our support to the U.S. Space Force, the National Reconnaissance Organization, and then also NASA, NOAA, Missile Defense Agency, and several others. So we've been around for 60 years of innovation. And what was interesting, this literally is our Zoom background for 60 years of innovation, which we celebrated during the global pandemic. We're supposed to have a nice celebration in the summertime, and so now I'm talking to a video screen with no faces to see. Hopefully soon I'll be able to look at faces again. But nonetheless, as you look back at our history, it started with inventing. I mean, it was the dawn of the space race and the space era, and experimenting. In fact, if you look at a good program to look at is Corona, which we failed the first 12 launches. Imagine getting a satellite program through Congress, whether it be NASA, NOAA, or Air Force today, where you failed the first 12 launches of that satellite. The 13th was a success, and then there were 100 plus successes of that satellite afterwards. If you don't know about Corona is a film camera, is driven by mechanisms, essentially. Film spirals through the system on mechanisms. Of course, there's electronics to drive some of the motors and so forth, but very little, if any, software at all. So that kind of is the beginning of space, where we really are driving analog electronics, and most of the logic is built into the electronics rather than the software. And then I think there was a real pivot, probably in the late 70s, 80s, where we started building and normalizing some of these systems you may have heard of, like the Defense Surveillance Program. That's our early missile warning system. Then Millstar, where we did communications. So there's now a lot of electronics embedded in the systems. We're getting our first analog focal plane array. I say analog because it wasn't converted to bits until it went down to the ground. So it's an analog signal through the whole processing chain. So there was no software. There was very complex analog electronics, but there is starting to become flight software to control those satellites and to do the basic operations. A lot of ASICs to do anything with extensive processing, just because we didn't have the speed of general processors at the time. And that's really where we kind of normalize the systems that we think of today. Some of the core U.S. Space Force systems of missile warning comm, and this is the beginning of GPS. And then, so that's kind of phase two. Phase three, I think, occurred in sort of the 90s and even into the 2000s, where we really switched out a lot of that circuitry for software. We started putting more general purpose processors on board, adding software into the systems to add smarts. This also created new issues with how do we qualify that software. Of course, software was always on a critical path, not necessarily because of the software fault, but software also has to interface with everything. So kind of everything else has to be there before you can finalize the software. And software is often very useful in fixing hardware flaws. So it started to look at how do we efficiently manage the software development cycle for reuse, for modularity. How do we test it in a way where we can test all excursions? What are the scripts we need to do to test all the functionality to make sure we don't get in some kind of loop? So that was kind of phase three. And I think we're moving into phase four, or maybe in phase four right now. And that's really the computational power has increased radically. We now, instead of hundreds of telemetry points, we're bringing down thousands of telemetry points on every satellite. We've got some things that are now being designed from scratch. If you look at Falcon 9, totally different design from some of our legacy rockets, where they can build in telemetry and in situ testing. We're doing that in several of the new generation satellites. A lot of autogen for code. And I think in this generation, we really had to start paying attention to supply chain and cyber. And that, again, changed with another big change. With thousands of telemetry points, you can now start to look at things like machine learning and AI, fleet surveillance on the health and status of the whole fleet. A lot of that is still done on the ground, not in the flight software. So, that's really, I think that's the next pivot, right? Is when we start to push some of that to the edge and we start getting software defined everything, including out in the satellite. We're starting to see some of this in our experimental programs now. Like in the space segment, one of the things we're building now is the navigation technology satellite. It's -3. It's a third satellite, but we built 1 and 2 back in the, I think, late 70s, early 80s. So we haven't done anything in GPS in decades. And this is putting in a software-defined radio inside of GPS so that we can change the GPS waveform and the GPS signal on the fly. That's really enabling. It's also a configuration issue as well, because if you're changing the transmitter waveform, you have to also reach back in and change the user terminals and have all of that synchronized. So big new challenges. Another good example of this is some of our ground segments have gone, at least in a demo sense, we've pushed those completely to the cloud. Recent demo we did was with the Joint Polar Satellite System, where we leased the ground terminal. Guess I won't name the competitor or the provider, since there are now lots of people getting into this market. but we leased the ground terminal from a cloud provider who took the data, used our decryptors, pushed the data to the cloud, where we could then exploit that with software, and all of our data users and analysts could come in and do that in the cloud as well. And the cloud provided the dissemination system on the back end to get it to the next user in the pipeline for that, in this case, that weather data. I see that being big in the next generation of satellites as well. Last example I'll give is a little receiver we built called the blind suppression system. And it's just a GPS. It's actually a front end on a GPS receiver. So it goes between the antenna and the GPS receiver itself. And it's a blind receiver. It looks for L-band, I'll call it noise, but the noise could be intentional jamming. It then characterizes that noise in real time and puts in software definable filters. And it's modifying those filters real time based on the RF environment that receiver is operating in. So you can see I just gave 3 examples: satellite, ground, and user terminal, all of them totally software definable. That's the next pivot. I think we're just now starting to enter. I mean, we're in it, but we haven't really deployed those systems in an operational sense yet. I do think, you know, if we get to the sort of the one end state I see, maybe kind of a dream state, is if you look at some of the phased array technologies now, they are becoming much more robust. If you can get a wideband or broadband phased array technology driven by a software backend, you're now got a converter, basically an RF to bits converter that can be used for a bunch of applications. Starlink, of course, is a phased array system where they can form hundreds or thousands of beams and communicate with all their users. But they're doing that primarily, actually, I don't know the details of the code. Usually you're doing that with ASIC design because of the amount of processing needed. If you can get the processing up and have that software definable, you could now start to look at that being a multi-mission platform. And whether that RF energy is communicating bits or sending a nav signal or putting down a radar signal, and then using the receive modules to measure the reflection. You could start to envision a real multi-mission broadband phased array kind of construct in the future that's totally software definable. I think that really is our next phase. So that's kind of a long way to introduce aerospace, but we've sort of, over 60 years, we really have seen the migration. And even in our little Zoom, memorial or commemorative Zoom background, you could see this thing's obviously, and I don't know if you can see, probably can't see my arrow, but if you look in there, you'll see several analog devices that were purely analog and electronics, and kind of a conversion to computation over the years. And of course, now everything is software driven. So I think we're actually on an incredible, exciting, the most exciting time in space, at least in my career in the space arena. And maybe it's in any field right now, because there's just so much going on in software and the acceleration of technology. Let's go to the next slide. So what does that mean for space? Space is got a lot of legacy tail. I mentioned some of that, right? We depend on GPS. Those signals were designed 30 years ago. We're trying to pivot from some of the old ways we've bought systems. And what you're seeing on this chart, on that top line, is our typical government first unit. We're typically bleeding edge, or have been bleeding edge. We've been inventing these missions, whether they're remote sensing, secure comms, or nav. And as you invent something, there's a lot of development time. Most of you know that first 5 years isn't development time. There's some development in there, but whether you're NASA, NOAA, or Space Force, there's also congressional budgeting time. And a lot of that pre-ATP is getting enough stakeholder and mission support to view this as a wise investment. But still, there's an 8-year cycle generally between we decide we're ready to go build something and launching it. And given all the change I just talked about, there's no way an 8-year cycle can keep pace with the technology and can keep pace with the threat. In fact, if you look at an 8-year cycle and just look at what the compute power has done, we'll call it CAR, software instead of flight software. I mean, if you look at the autonomous vehicle industrial base, and you look at a vehicle we started building 8 years ago, a space vehicle we started building and putting flight software in place 8 years ago, and what the car industry is doing in autonomous vehicles 8 years later, it's not sustainable. People are going to ask, why is the billion-dollar satellite literally 2 orders of magnitude behind in compute power? So we have to get to a different basis. One of the things we've been pushing is trying to get part of our industrial complex, our space enterprise, on a production footing. That third line down is what our average government production vehicle is. And in fact, I think we're beating that right now on GPS-3. I think it's closer to the third. I'm sorry, I said the third. I meant the second line down. But I think our 3F vehicle, our GPS-3 vehicle is closer to that third line, which is what a typical commercial geosatcom could do. All of these are predicated on what I'll say, I don't want to say old school, but basically the geosynchronous kind of satellites, the big school bus size satellites. This, of course, all changes with the P-LEO system, the proliferated LEO systems, which are being fielded today. One other thing I want to mention on this chart before I move on is just, if you look at the change on the far right, the only thing that can change at the rate of technology and the threat is software. So we have to figure out ways to be able to get our software refresh faster and be able to roll capability into the satellites to deal with either new capabilities that we need, either for market or for a mission or science, or a threat that's being posed to the satellite. So I think flight software is right in the middle of this in terms of enabling the kind of pace we need in the future. So let me just talk a little bit about some of the key technologies I see that are driving us to move to a faster tempo in terms of satellite deployment. Most of the technologies we're seeing are not occurring in the aerospace sector. That in itself is kind of new. I mean, we drove transponders, we drove technology for digital focal planes. Now that's not true at all. And we're trying to leverage technologies that are going on in other sectors. So microelectronics, of course, a big one that's driving everybody's life. But these are things like enabling software programmable radios where we can actually change the waveform and change the mission on the fly. I've already mentioned phased arrays. So that's miniaturizing both the transmitter receiver, the antenna structure, and then being able to integrate it into an integrated circuit backend. Often, like I said, right now, that's an ASIC, but if we can get to the point where that's a general purpose processor, we can get to the point where or even FPGAs, we can get to the point where we can do reprogrammability of that phased array and potentially flex the mission of the phased array in space. Of course, miniaturization of all that microelectronics is a big driver, both in our commercial products and certainly right now, anyways, in the mass of the satellite. But one of the real challenges that we all face is high rail and radiation parts. If I'm going to spend, on that top line, that 8-year development cycle and $1 billion on a satellite, it's actually got to work for 10 or 15 years. How do we deal with that paradox? Are there other ways? Do we try to leverage the commercial technology and make it rad hard? Do we put lead around it? Or do we try to go to a different footing where we're replacing these things every year or two? The commercial electronics are cheap enough where we can put them in parallel and do voting architectures. I mean, that's something our industry still has to deal with. Otherwise, we're going to get left behind by the pace of technology in the other sectors. The microelectronics, I think, are enabling mesh networks. We're seeing proliferation of nodes, across. You pick a network and a mission, and I mean that in the broad context, medical, investing. They've developed networks, and those networks are often software definable, but they've done that through standards, and we're often lacking that in the space arena. And that's something we're going to have to continue to develop. Once you put those two elements in place, microelectronics and mesh networks, it's software that drives all that. And we're starting to adopt DevSecOps or DevOps. We put the sec for security in the middle of it. in a lot of our, certainly in most of our ground systems now. But how do we do that in space? How do we virtualize the processor for flight software? Can we containerize code and put microservices in place on a spacecraft bus? If you could do all of those things, then I think autonomy starts to really drive. And that's kind of that last pivot I was talking about when I was going through the history of aerospace and software. That starts to allow edge processing, where we can start to put machine learning or artificial intelligence. We can use that for just simple things like bus network monitoring for cyber intrusion, or we can use it for more complex things, like I'm looking at a remote sensing scene and there's change happening. What is that change? In that case, you've actually got to train the AI and train the machine learning. But if I could push that to the edge, I can now downlink that directly to a user who needs to know there's change happening on the Earth. But all this is going to take a much stronger set of standards and modular or digital engineering across the space segment. We've got some really good examples of this, but they're really old. Things like the Air Force SIGLIS, or satellite control network, which drove the S-band SIGLIS standard that many people still use today, 30, 40 years later, for our telemetry links. 1553 is another one, but really, I mean, that's the state of our spacecraft bus. So are there new standards we can push to keep pace with the technology the commercial side is developing? The other key in getting rid of that really long development timeline and keeping the production lines reliable is taking advantage of this autonomy, or some of this automation in our actual design and mission assurance processes. So things like automated inspection and test, building that into the system. I mentioned the fact that we literally have thousands of telemetry points coming off these satellites now. How do I use big data to look for out-of-family instances rather than trying to test everything and test every configuration? Look for trends in the telemetry data. Obviously, the same thing needs to be done on the software side. There's obviously some of the auto generation capabilities, but moreover, how do I build software in the loop where I can emulate the flight processor and emulate all of the widgets connected to the flight software processor in a high enough fidelity that I can be comfortable that code's ready to go, and and risk $1 billion asset. And can I move it from that emulated software in the loop to a hardware in the loop where I'm on the engineering unit, and then move it into flight? And further, we do a little bit of that today, but it's not mechanized. How do I keep that in sustainment for the next decade, so that every year or 6 months I'm pushing out a patch that's gone through? Right now we build very expensive flat sats, and we typically build them for every mission. We need to figure out a way where we're doing that for a platform that supports multiple missions. And of course, shifting the software pipelines into the cloud, and we're doing that on many of the ground systems. I'll mention one kind of unique application of this kind of automation where we're doing additive manufacturing for critical pieces, say like a turbo pump, the turbine in a rocket turbo pump. We're actually able to go in and put cameras at different spectral bands and measure and monitor the metal laydown in situ. Now think about that. This might take 30 hours, to additively manufacture a turbine. So you're getting gigabytes, terabytes of data of these monitors looking at every bit of metal being laid down in the machine. But we can use machine learning to sift through that to look for any impurities or flaws in the raw material. And likewise, we can do that on the machine tool itself, if there's any error in the software driving it, or in the laser power supply source. Seems trivial, but if you're going to if you're going to spend 30 hours and then have to go test this thing, this is a way to get rid of testing. And if you do have a slight impurity in the raw material, or you do have a power hiccup in the machine tool, you can shut down, repair in situ with the machine tool, and then finish the build cycle. Those are the kinds of things that I see software driving in the future and changing the way we build these systems. If we go to the next slide, this was, I meant to bring this up earlier, but this just shows what you can accomplish with autonomy. I mean, this is obviously natural autonomy, but it's amazing what a number of simple I guess birds aren't simple, but what a number of devices, or in this case, birds operating in unison can create. And I do think we're going to see more autonomy solutions like that in the future. Let's go ahead and jump to the next slide. So in addition to all that technology, we're seeing commercialization and democratization of space like we've never seen it before. I mean, literally thousands of more vehicles in orbit. We're seeing reduced launch cost. We've seen the launch cost go down by about a third. You got Starship and Blue Origin on the, both looking at putting people in space. If they get there, that'll be heavy lift. And I think we'll see another drop of a third. So it's an order of magnitude kind of reduction in launch over a decade. That's game changing. That changes the whole mass calculus. What you're looking at on the screen is pretty cool. I give credit to Elias there. You can see this is right out of his Twitter feed. What you're looking at is the buildup of the Starlink constellation over time. And it looks much like the birds in the sense that you're seeing systems being deployed. You're seeing them spread out. Question is how much autonomy is in here and how much person in the loop. That's a question for SpaceX. But it does convey the complexity and autonomy you're going to need if they're going to deploy 10,000 of these. I think in this count, this is probably nearing 1,000. And this is just Starlink, right? We've got companies like Planet doing the same thing for remote sensing. We've got companies like Spire doing the same thing for SIGINT, signals intelligence, where they're capturing RF signals. And then I already mentioned the tourism push. So there's some amazing things going on in the commercial sector. One of the big things I think that's enabling this is the size and scale. These are not school buses. These are things that you can put on a table, you can push around, you can have people work on them and integrate them in a much simpler fashion. It allows a real big change in production efficiencies. The other thing, if you're building 1,000 of something, or even, I'll say even 40 or 50 of something, you can spend a little time up front thinking about autonomous test and really reduce the back end testing that's required for these big school bus billion-dollar assets. And that's enabling as well. I think on the flight software front, though, they introduce an interesting challenge because, as I mentioned, we want to evolve these designs, evolve with the pace of technology. That means these satellites are changing at 6 months, 1 year, whatever the right center is, as you're bringing in new capability, a new GPS receiver, a new star tracker, a new phased array. And the software has to evolve with the hardware baseline. And oh, by the way, you're also flying all of those old baselines. So you have to maintain configuration control across the fleet. This is kind of a new issue for aerospace. I mean, we certainly do it in the aircraft world, but in the space sector, we even, take GPS, there's 36 satellites, right? And we kind of maintain individual code baselines for each spacecraft. We don't try to maintain the fleet-wide option. And 36 is kind of easy enough to do that. You can't do that with 1,000 satellites. So I think flight software configuration controls, we get into these big enterprises, is going to be a growing interest as well. It's interesting because we don't know what the business viability is on these yet. It's looking pretty good. It's pretty impressive to see what people have accomplished. I think we're going to make it this time. I say this time. I spent a couple of years in Tucson, Arizona, not Tucson, Tempe, Arizona, watching Iridiums come through and designing teledesic, right? And we kind of missed the market on that constellation. So the jury's still out to see how many of these are going to be successful. I think we're going to have successful players this time in every one of the mission segments. So it's really great to see. So that's kind of change two. The commercialization and democratization that's driving a need to change how we do flight software. If we go to the next slide, the third element that I think is pretty critical is the adversary. And as I said, we didn't even talk about this 5 years ago. And in my introductory remarks, I gave a couple examples of where we've publicly seen adversaries deploying offensive systems that can harm satellites or deny access to the satellite signals. that doesn't seem to be going away. And when you look at the kind of economic dependence on something like GPS, it really is critical infrastructure. Just as critical as the power grid, just as critical as the internet, just as critical, as our transportation networks. So it's something we really have to start paying attention to. I mean, you've all seen the rollout of the United States Space Force. It's the reason the Space Force was created. It was to kind of change the mindset that we're not just there operating a static service like GPS or a comlink or eyes in the sky for missile warning. We're actually there in a domain that is now contested, and we need to react to those threats and make sure we can continue to provide the services our users have come to depend on. There's also, it's not really shown on here, but there's also the congested aspect of this too. I just showed 1,000 satellites orbiting. You might have seen in the press just recently, the Electron rocket put up an OHB, I think it was OHB satellite that was on a collision course with OneWeb. The space traffic management part of this becomes a big deal as well. And actually, back to software, if we're even a third successful with the amount of satellites that have registered with the FCC, you're going to have autonomous space domain awareness in the LEO environment and autonomous collision avoidance. It won't work otherwise. Otherwise, you're going to be spending all your time doing conjunction analysis and a person actually trying to figure out what the right avoidance maneuver is. And you don't have enough people or enough hours to do that, given the projections of satellites in orbit. There's one threat on here that's particularly interesting to the flight software community, and of course that's the cyber threat. And we've got a lot of work to do in sort of reinventing what it means to protect the flight software, or I'll call it vehicle software, right? Autonomous vehicles are probably going to beat us to the punch by a big margin on this. 5 years, a decade ago, anybody could plug an OBD2 port into a car and get onto the car network. A lot of the vendors even started putting Bluetooth access to that network, so you could come into it from the outside, and it wasn't protected. I mean, the protection was having a serial number registered with your heads-up unit on your radio so that no one stole your radio. That's not much protection from a cyber sense on the network side. Autonomous vehicles, obviously, with safety of life, have to deal with that in a much more direct way. And we're going to have to do the same thing on our satellites. We've started experimenting with onboard monitoring and mitigation systems where we're tracking network traffic, looking for anomalies on the network traffic, and putting in mitigations in place to shut down the system. I don't know, we might even go back to having more what I'll call analog safe modes. Many of our satellites flew very rudimentary processors or even ASICs or electronics for their safe mode, where you just, dumb system to remain sun pointing until you could come in and find out what was going on the flight software. I could see us even making sure those systems are in there to avoid having a cyber takedown. We have been drafting a standard for this. Maybe Andy Waltham, some of you may know Andy, he's been working a standard for satellite network buses and the cyber defenses on those buses. And maybe I'll encourage him to get out here next year and present that. Hopefully by then it will have gone final and we can share that with industry. If you go to the next slide, this is just kind of an interesting side note, just to give you a feel for how serious we take this. This is something we did this summer with DEF CON. DEF CON is an area that the government typically stayed away from. I think General Hayden, NSA, probably 5 years ago, I think was the first time, it could have been longer than that, 6 years ago. He went to the conference. After that, the Air Force followed with some aircraft components. So we showed up this year with some satellites. Again, I'm following my Twitter reference source. So here's a Twitter feed from the group, and we actually took some breadboard CubeSats. It really wasn't a hack-a-sat. It says hack-a-sat there. It was really a capture the flag competition to get people thinking about the satellite the space domain and what the satellite configurations look like. So we had a breadboard CubeSat, we had a ground site, we had an RF link, and competitors had a series of events they had to accomplish. In fact, that is the 8 finalist teams that got to go in and try to capture the flag in the satellite, and the columns are the various events that they accomplished. And the winner, we took the winner's command stream and we were able to convert that and use it to actually command a CubeSat. But it's really more of a learning experience to learn what are the features and functions of a satellite that a cyber attack might go after. And the team is spinning up for a same version of this in 2021. And I assume we'll increase complexity of this. Like I said, the aircraft components with the Air Force are next door, but beyond that, there's cars sitting there that hackers are trying to get into. There's voting machines. So it's something we as an industry are probably a little late to the game in, because we felt somewhat protected and encrypted and firewalled. But as the IT becomes more pervasive, as cloud becomes more pervasive, it's something we've really got to pay attention to. So what does all this mean in terms of flight software? As I said, I think flight software is critical to being able to respond to this, but I think we do need some more standardized protocols and approaches for communicating and messaging across our space enterprise. If you go to the next slide, this is a reference. It might be worth going out and taking a look at. This is from Dr. Will Roper's feed and a paper they put out. He was a secretary under Secretary of Air Force acquisition. So he was in charge of acquisition for the Air Force. And he put out a kind of a call to really look at digital engineering and make sure we're employing that or applying that to the best extent possible. If you think about all the things I just talked about, you really can't do them without having a digital engineering process, both for test and assurance and for just configuration control because of the complexity involved. And so this paper actually talks about how they went from an electronic airplane and simulation space to the hardware. We're trying to do similar things on the space side as well. I guess the last thing I wanted to leave you with before I talk a little bit about that little demo we've been working on is just the test process. Right now, the U.S. Space Force and many of the other government entities have a development test program and an operational test program. And that is not, it's got to change. Right now, it takes us anywhere from a year to 2 years to get through that process. That means the software is a year to 2 years old before it goes into operations. And given the rate of change that I described earlier, we have to figure out a way to verify the mission assurance of that software sort of in situ as it's being developed through a digital chain, in that emulation and simulation space, maybe a flat sat, but we can't afford to deploy it on a parallel string and test it for 6 months to a year. We just don't have the kind of time when you look at the pace of technology, which also drives the pace of the threat. There's several enablers for that. We talked DevSecOps earlier. That can, of course, help the flight software updates and evolution, but we need to figure out how to get that into the test programs. There's the modularity, and can we get a set of open standards that are loosely coupled and microservices on board the satellite so we can just upgrade certain portions of it. I mean, I'll give you one example that I was kind of dumbfounded, and this was might be a decade ago now. But we had some Parrot UAVs that we gave to some sixth graders and set up a little demo with them. And these sixth graders were able to do mission management threads on the Parrot UAV in about 2 or 3 days. They were using the UAV itself, an API for the Parrot UAV, a Wi-Fi connection, a Wi-Fi router, a laptop, Node.js was a software port, and an open source mission management software. And these are sixth graders, and they linked all that stuff together. I mean, of course, there's all kinds of instructions and YouTube videos that tell you how to do that online for the sixth graders. But try to do that with a satellite system. We don't have those kinds of standards that are out there today. Of course, we got 1553 and we got the SIGLA standard, but those have not evolved in decades. So what is the next generation of modularity that our systems need? And I think some of the digital engineering aspects that Dr. Roper points out in this paper go to some of that. Let me jump down to the next slide and just give you a quick summary of this slingshot activity. And you'll see several of the things I talked about. This is, as I said, we've launched a lot of CubeSats. This is moving up into a 12U class and giving us the kind of our next generation test platform. A lot of our CubeSats to date, well, we started out at about a third of a U back 20 years ago. And our current test platform is a 3U system. And now we're moving to this 12U system. Also, you know, some of the standards were developed at Aerospace. It's commercial now. So this bus is a Blue Canyon bus. You know, there's no need for us to develop our bus. That technology has been transitioned to industry. So now we're working on the modularity of this satellite system and trying to make sure we can bring new technologies in quickly. All the things I talked about. How do we get autonomy on board? I mean, just to give you some examples, there's a lot of mechanical and electrical interfaces. I won't bore you with those, but the whole thing runs on Ethernet, and all that's plug and play. But we're able to quickly bring in, you know, state-of-the-art GPU processors so that we can run machine learning and artificial intelligence algorithms that are much more advanced than what we can put on the billion-dollar assets, because we can push that processing power. We've got the UltraScale Plus FPGAs, so we can do quick experiments with that. We've got secure ARM-based chips on here that we can play with. There's a software-definable radar or radio that we can start to do experiments with. We've got software-based crypto, so we can actually experiment with the crypto link. A lot of that processing capability also allows us to put in onboard malware detection, network trackers, looking for any kind of cyber intrusion. With all that processing, we've got a reconfigurable autonomous ACS that can do prox ops. It can do just standard. It's got it's got a bunch of modes built into it. And it's kind of a turnkey box with the sensors and reaction devices. We're playing around with it or basically it's an AIS, an automated identification system like they have on ships. We call it Blinker, but it's basically a GPS transponder to identify all these objects in space to help with that space traffic management problem that we talked about earlier. If you go to the next slide. So this is kind of a way we're trying to bring that speed and agility so that we can evolve quickly. We started this about a year ago. I think we launched at the end of this calendar year. It's about an 18-month, maybe a little longer than 18-month turn on this first satellite. But the idea is now the platform's there, so we can bring in modular payloads and modular experiments. And actually, there's several experiments on each one of these. So it's a production-like run. We'll continue to buy that Blue Canyon bus. We'll continue to put some of these commercial modules in a production sense, and then we'll bring in innovation, new flight software. Oh, I forgot to mention, they're actually running Kubernetes in the cloud on board the satellite here as well. It's providing several of the services for the payloads. So it's just a great platform to experiment and look at, you know, what does the next generation space system look like, but equally important, how does the flight software command or control all of it, and what processing kind of ecosystem can it live within? So with that, I wanted to leave a little bit of time for questions. So why don't I turn it over to Chris, or ask Chris if there have been any questions.
Yeah, thanks, Kevin. We do have a couple of questions. The first one, I think you did touch on several of these things throughout your talk, but I'll go ahead and read the question and you can touch on any of these things that you think. So there was a comment on the ambition of a 1 year software update. So MSLs are hope considered 19 months start to install as super fast. So how do you cut down that time without sacrificing safety or trust in the software?
So I think what we have to do, I mean, one, we have to, at least on the US Space Force side, we have to completely change our process because we have so many steps. Now, how do I do that without risking quality? I think there are a couple ways. One, so maybe a couple approaches. One, I mentioned the simulation, emulation, and hardware in the loop. I think you certainly need that. And if you can develop in parallel in those three domains, I think that helps bring software forward on a quicker pace. The other is to bin your software, in the sense that some software, like I probably don't want you messing with, we call it dead bus mode. If you've lost battery power and you're going into a dead bus mode, I don't want to end up in a dead bus mode I can't get out of. There might be other critical functions. Maybe it's the timing on an imagery satellite, functions that you wouldn't mess with without going through that full process. But there might be other systems, like if you're trying to push edge processing on an exploitation of a signal, maybe I can take a little bit of risk there and make sure the user understands the risk. Maybe I'm on a commercial SIGINT platform, and I'm trying to figure out if it's an AIS signal or noise, and I just want to basically type the signals. I can allow error to creep into the system. So I think those are two ways. One is to make sure you've got a high fidelity software, hardware, and actual flat sat simulator if you've got a high reliability mission. I think you said it sounded like that was one of the high dollar exploration missions. And then the second is to bin it. There is some software where probably you're not going to take risks on. It's going to take the 18 months, but there are other elements of the satellite that you can use as more of a sandbox. Those are two approaches we've been playing with, and that's actually even on the slingshot example. We've actually binned the software into different categories. There's the experimental side of the bus and the side that maintains housekeeping and safe mode.
Yeah, and maybe I just want to throw in maybe a different word in there for binning, because sometimes it's the term partition has been used, and so there's software technologies to help, I think, do some of those things that you're talking about with respect to partitioning. One comment that I had was really with increasing the pace and agility while also having the concurrent cybersecurity concern, that these two things are kind of opposing in nature, that the more we standardize in general, make our systems more general purpose and easier to upgrade, lower those barriers, at the same time, we may be introducing additional cybersecurity concerns.
Yeah, cybersecurity is a huge challenge. And it's both sides of it, right? If you sort of stay locked in your legacy system, you don't know whether there are new vulnerabilities as the rest of the IT infrastructure stack progresses. And if you constantly are upgrading at the bleeding edge of commercial, you may have the same issue. So how do you balance that? And I think we're also at the point where like I mentioned, you can't just assume you're firewalled anymore, or you've got literally a air disconnect. Our approach to that has been trying to do testing in parallel as kind of a sustainment, as a ongoing sustainment, in the sense that you have a team. In the Space Force parlance, you'd call it the red team, but any kind of team that's looking for vulnerabilities on a continual basis, and that means that's just part of the normal sustainment mode, and that's part of this pivot to the threat I was talking about. We probably talked more about capability. We did talk a lot more about capability we could put up in space, say a decade ago, than we did making sure the capability we have up there is protected and going to be viable throughout an attack.
Yeah, and I think you also touched on that. Yeah, that continuous and that integrated, automated testing, and really making sure that is streamlined and embedded in the process is going to be absolutely necessary.
Yeah, I think the big key on that is production efficiencies. Other industries are able to do that because they're in production, and Actually, it's an interesting. I'm coming from my mindset where our primary customer is the Space Force and IC. It's interesting to think about, are there science platforms that are similar where you get in production on a science platform, so you're not reinventing the platform each time if you're working on a NASA mission.
Yeah, absolutely. Trying to figure out what the commonality is and supporting multiple missions with as much in common as possible. Let's see. One other question from DJ, one of our speakers yesterday. Successful cyber attacks on satellites are quickly classified, at least in terms of his experience. And how can we make convincing cases with respect to hardening our systems without public data, in order to base our decisions on? And are there case studies available?
That's a good question. I would say it was challenging 4 or 5 years ago. I would think now you can go to any press release and you can pick up a quote from General Raymond talking about how essential it is that all of our space assets, not just the Space Force, but NASA, civil, commercial, are all very aware of the cyber threat. He has certainly made those more public. The fact that we're starting to show up at places like DEF CON is a real sea change as well. Now the question is, when are we going to put an operational system in the middle of DEF CON and expose potential vulnerabilities? That seems like a big path, right? Or a big ways to go yet. So I understand the complexity, but I think the whole fact that we have a Space Force and you have General Raymond articulating the need, and actually that one chart I had in there showing the threats to the space system, that's a chart we would not have even talked about a few years ago, and that is it comes directly out of a Defense Intelligence Agency report that was released about a year and a half ago. And it's got it's a 40-page report that was released to the public. So I do think we're talking about them more. They're not all classified. Maybe the details are. One of the challenges we face is making sure the supply chain is completely aware of issues we find. And we do have processes in place to do that within the supply chain. But as the supply chain grows and we bring in more commercial suppliers, how do we make sure they're also aware of issues? And that is something we struggle with.
All right, great. So that's the 2 questions we have. Are there any other questions for Kevin Bell while we got him? This is our opportunity. All right. Well, thank you so much. That was a very thought-provoking talk and a lot of significant challenges going forward. Thank you so much, Kevin.
All right. Thank you, Chris. Thanks everyone for the time.